So if we look at the contents of the webinar here to start off, I want to do an introduction to Bernoulli's principle, just down and dirty definition of it, and a Venturi validation example. And we also want to look at a muffler design. So we're going to look at a stock and or OEM design, and then also an aftermarket design. And then just kind of follow up with a summary there as well. So let's go ahead and look at the introduction to Bernoulli's principle. So essentially, Bernoulli's principle, it's very common in any engineering fluids course that you take, but it basically specifies that for an ideal fluid, any increase in velocity, there's a decrease in pressure, and vice versa. And this is actually based on two essential equations, one for incompressible fluid flow and the other for compressible fluid flow that you see down there. So what I want to do is with the Venturi example, which you see at the bottom of the screen here, show this inside of flow simulation. So let's go ahead and jump into SOLIDWORKS. So everyone here is familiar with the SOLIDWORKS interface. We have the command manager up at the top, and when you add in the flow simulation add-in, you get a new command manager. And we have this Venturi set up. There's a lid on either end, basically capping this volume. And we want to start off with telling the software what are our inputs, what are our boundary conditions. And Flow makes this actually really nice because it gives us a wizard to do this. So I'm going to go ahead and start my wizard, and I can name this whatever I want to name. And I'm going to call this setup. Using the current configuration, all of your Flow projects, which are housed over here on the Flow tab, are under your configurations. I'm going to go ahead and say next. Actually, we can just call this project 2, let's say. Next thing that we want to do is we want to set up our unit system. So our units here, we can either do feet pound per second, inch pound per second, or if we wanted to, we can do a custom group of units. So in here, if I wanted length instead of inches to be in feet, we can do that, or meters, or millimeters, whatever unit of length we want, even down to a rod, which is something that's not necessarily common, or chain, or cab, but more common inch, or centimeter, or foot, in and along those lines. So we can change, or we can select our standards from here. And actually I want to switch this back to inches at this point. Next step is to tell the software whether this is an internal or an external flow. We can handle both inside of flow simulation. This is actually going to be an internal flow. We can also handle heat conduction in solids. We have conjugate heat transfer inside of flow. So conduction, convection, and radiation, which we can turn radiation on here as well. We can do a transient analysis or steady state, which is what we're going to do. So I'm not going to turn on my time dependency. I can include any natural buoyancy effects due to gravity as well, and any rotational frames. For this case, we're going to use the stock internal flow. At this point, I want to tell the software what liquid we want to use. And in this case, I actually want to use water, so I'm going to be utilizing a fluid. So I'm going to add that in. All of our properties of water, such as the density, viscosity, things like that, those are all housed inside a database, which I will show you. I want laminar and turbulent flow. We can handle just laminar or just turbulent or both. So I actually want both to be solved out. And then the next step is to tell the software our wall conditions. So if this was a cast part, let's say there would be a specific roughness associated with that would cause eddies along the wall. We're going to assume a perfectly adiabatic wall, so there's no thermal conduction, even though we're not even dealing with thermal in this analysis, and a 0 micron, so it's a perfect wall scenario. These are my initial boundary conditions, so I'm assuming atmospheric pressure is at sea level, and temperature is roughly room temperature, 68 degrees. Once we select next, it puts us into our meshing refinement. We have 1 through 8 are levels of resolution. 3 is the default. It actually does a very good job of recognizing the areas that are thinnest and applying the proper amount of cells across that boundary. We have full control of that over that as well. Basically, when I select Finish, what ends up happening is SOLIDWORKS automatically does the Boolean operation behind the scenes to give me my internal volume here, because it is indeed capped with 2 lids. Now, I have a section view turned on so we can see inside this Venturi. I can turn off this computational domain, or actually essentially hide it, and I'm also going to hide my global coordinate system. Just cleans up the view a little bit. From here, it's a matter of adding our boundary conditions. So I want to add a specific flow rate coming in on this end. So we can do an inlet mass flow rate, we can do a volumetric flow rate, or a velocity. So we'll do a mass flow rate, and these are pounds per second. So I'm going to specify 2 pounds per second inlet. My outlet, I'm going to insert a new boundary condition, and it's going to be a pressure outlet to environmental pressure on the back side. And notice my environmental pressure carried over from my initial settings as well. At this point, we have an inlet and outlet, a volume that we're putting or addressing flow through. It's a matter now of running this. When I run this, I can mesh and solve or just mesh. So what I want to do is actually show you just the meshing process. So I'm going to select Run. It's going to come up with the initial mesh. Now there are a wide variety of mesh tools that are available inside of Flow. I'm just using the default mesh at this point. I just wanted to show you how well it meshes right from the beginning. So it generated the mesh normally, gives me a partial cell and a fluid cell count. So inside of Flow, we have 3 types of cells. We have solid, we have partial, which is the boundary layer between the solid and the fluid, and then fluid cells as well. And if we look at our mesh, I can show this in a cut plot about the right plane. And we see that Flow automatically narrowed down the mesh in the area of this neck in the Venturi. We have a good 4 fluid cells, which is a steadfast rule in any CFD scenario of fluid cells across any opening. So right away, just leaving everything at the default setting inside of Flow, we're getting a fairly refined mesh to start with. So we're getting good results at this point. I'm actually going to switch to a already solved scenario. The run wouldn't take too long. I believe this one was about a 5 to 6 minutes. But because it's already solved, we can get right into the results. So I can load my results here. And the first thing that we want to look at is our cut plots. And my first cut plot is pressure. So I applied the mesh, ran the results, and I got my pressure across my Venturi. Again, my inlet mass flow rate is on the left at 2 pounds per second. My outlet is in environmental pressure. I also added things in this study that I didn't add in the previous study. And these are items that are called goals. So we can tell the software specific goals that we're looking for. And I actually was looking for total pressure, static pressure, and dynamic pressure at 3 points. And if you look at this sketch line that I have down the middle of this model, let me hide this out. I actually have these points, which are typical points for these measurements inside of a Venturi if we were actually doing this as a physical test. So I looked for static pressure, total pressure, dynamic pressure at this point. So it'd be my pressure point 1. I also look for velocity at that point and at the point in the middle. So I have a velocity 1 and a velocity 2. And then I also have an equation goal. So based on those pressures, so I have a dynamic pressure at point 1, a dynamic pressure at point 2. They're subtracted from each other. That gives me my pressure differential. So what I want to show you here is let's look at the pressure plot. And if we look, we have a high pressure here, a low pressure in the neck, and then it expands out to increase the pressure again. Let's go ahead and look at the velocity plot. So if I show my velocity plot and I hide my pressure plot, look at what we have. We actually have the reverse. We have a lower velocity in the area of high pressure, and we have a high velocity in the area of low pressure, and it tapers out. So we're receiving exactly what Bernoulli predicts, right? He's indicating that an area of low pressure is going to have a high velocity and vice versa. So simulation is actually showing that by these two plots. So the other question is, we want to verify this. We want to verify that our results are good with a hand calculation, essentially. It's a simple example, so we just want to examine that. If I look at my goal plots, I can specifically look at, I want to see my velocities, and I want to see my equation goal, which was a pressure difference. If I select show here, it gives me my variables down here. My velocity is 1.3 at 0.1. My velocity is increasing to 2.8 here. And my pressure difference is 5.9. Okay, so remember that number of 5.9. If we go back into my presentation and we look at our next slide, what I used was a modified Bernoulli equation. This is right out of my fluid mechanics book from college. 2 pounds per second inlet into the Venturi. I have my density, which is 1.936 slugs per feet cubed. And my velocities, the 1.3 and the 2.8, came out of flow. When we do this as a hand calculation, we're getting 5.9 pounds per foot squared. So we just verify the pressure difference by hand with this modified Bernoulli equation, again, right out of an example out of a textbook, right inside of flow. So we gained a good validation for this principle. We want to then apply this to a muffler design. We want to see the difference between two different mufflers.